Hello, Sarthak. Can you hear me?
Yes, sir. Yes, sir.
Can you see the screen?
Yes, sir.
Ask your classmate to join here.
Sir.
I think they are in another link.
Okay, sir.
Ask your classmates to join here. Hello, Sarthak. Has your friend joined?
No, sir. We are only two of them, sir.
In other thing, I saw that 10, 12 were there. I think you need to tell them, just send an WhatsApp message. I think they are waiting there.
No, sir. So I have messaged them, sir.
This is very important. Well, since I have lost time, I just want to tell you that what is. There is a problem with the Microsoft Teams. So that polygonal connectedness I talked about. I don't want to give the proof of that. I just should polygonal connectedness. Basically, it is done in a vector space. Okay. So basically, if you have this subset of this, then you say that polygonally connected. That is any 2 points, y1, y2, there exists, suppose this is y. So you get a finite number of line segments. Joining, these are called the line segments. Joining end to end, and this is y2. But this line segment will lie entirely inside y. Of course, inside x will be there, but my question is that then why? Because this is such a finite number of line segments joined end to end is called a polygon. This is called a polygon. And if y has this property, then y is called polygonally connected. Now look at the result. That this is important result what I have given, the theorem 11. X is a non-linear space. This is a generalization of the distance, the usual distance in Rn. So it's a non-linear space, and GB a non-empty open set. Then I have proved this, that the following are equivalent. Which is polygonally connected. Sarthak, have you sent the message to your friends?
Yes, sir.
Do they know?
Yes, sir. I have messaged them. They know the classes now.
I'm not going to prove it. Prove you can do that. I will tell you the technique on that. So G is path connected. And G is connected. So polygonally connect to that polygon, that is itself a continuous path. So that A implies B, B implies C, this is immediate. That I told you that from that. Okay. By theorem 10, A implies B, that every polygon connected in that. Theorem 10, the previous theorem. Okay. Okay. So that only C implies A, the proof is required. Since I don't have time, so I am just going to tell you that what is the idea of that. C implies how to the technique. I am talking about technique. Okay. So just see that this is a standard technique. Okay, so let me tell you that this technique, what I am using. Suppose you have a topological space. Suppose there is a technique. This technique you have used before in the exercises, the last semester also. Suppose you have it, and suppose you have this, and suppose this is given connected. Okay, and suppose this set A, E, this is non-empty. We prove it is closed as well as open. Suppose we prove it. Suppose we construct a subset and we prove this is both closed and open and it is non-empty. Then because of this your choice, E has to be X. That means in particularly suppose we're looking at a property P. Suppose you are writing this property P. Suppose E is those points. E satisfies P. And suppose at least one point satisfies P. So suppose first of all E not equal to phi, some property. And suppose at least one point satisfies this property, that means E is non-empty. Now we prove, suppose you can prove E is both closed and open. Then we, on the top of that you have connectedness. Then you must have equal to X. Now look, in this technique, what we proved that C implies is, we have used this technique. First of all, any point to point A, point to itself, that's the trivial path. Look, this you take basically this path, it's a line segment. This is called degenerated path point or interval, actually line segment. So this will be A. So starting with the point A can be always joined by a line segment. And look, what I did, simple as A. Suppose G is connected at fix a point T. Now look what I am doing. I am defining A. Here I am working on G, though it is a subset of this. I want to show that G is polygonally connected. That any 2 points of G can be joined by a polygonal path. So what I am doing, G is a subset of X. X need not be connected. I am looking for the connector. This is the subspace topology. Here the same metric will come. Okay, induced metric, submetric. So metric on the subset of that. It will give a metric, and that metric will give a metric here. Now look, A, you are taking this point. B belongs to G such that there exists a polygon from A to B. There it is not finished, lying entirely in G. Okay, right. Now I have taken a point A from A to A. So A itself belongs to A. So A is non-empty. Okay. Now you want to show that A, you show that A is both open and closed. And in fact, here you see that proof for closed is similar to open. Okay. So that A will be equal to G, since G is going to connect. So A will be G. That means it will be polygonal. But you say A equal to G, but I am joining each point to A. It's not a problem. Not between any two points. So suppose you can take two points, X, Y, and G. So A to X you have, suppose this is A, this, and this is A to Y. Then from X to Y if you come, then you take the inverse path of that. A to X, you take X to A. Okay. That basically will be changing of that. Okay. And then X to A, you get a not a line segment. X to A you get a polygon. X to A get a polygon. This polygon will be the opposite of the polygon you got from A to X, and then A to Y. So this way you will get a polygon. You will combine two polygons. Okay. In fact, this is the same technique you will be using here. Open and so this way any two points can be joined, so that G will be polygonally connected. And open, you will see that how do you show open. Here, be careful. It's not for any result. I have already assumed G is open. This is important. This you need. This you need. So that look how what is the technique in that. A you are taking this. Now look, so that I want to show that to show A is open, okay, right? That means any point will have to show an interior point. So take any B belongs to A. Now look what I am doing. Since B belongs to A, but A is a subset of G, but G is open in this one unit. So that since G is open, so B belongs to G. So there exists R greater than 0 such that B belongs to BR contained in G. Okay, right? Now look, what is the technique in that? Look, this is where if you take B R, this is the radius R, and this is inside everything in G. Okay. Now look, from A to B, A is here, suppose. A. So A to B. Now look. Now any point I am saying claim that actually this ball will have to be geometrically it's very evident. Have to be there. So this will be make sure this is open. Why? Okay, take a point here. That means you'll have to show this everything is here inside. Take a point here. Okay, now look from A to B, I have this polygon entirely lying in G, and from B to this, look, this is whole thing is inside G. So this line if you join, that will be also inside G. So you with this you join one more line segment. So that will be a polygon from A to this point. Call it Z. A to Z, and that will be lying entirely inside G. Okay, so that's the thing. That means this will be contained in this. Geometrically it is evident. Okay, so that's the thing. That's the way we prove. And same way you can prove that G minus A is open. Basically, the next thing when you prove that G minus A is open in G. So that's the proof. In fact, make sure that I have basically, though why do you say that, but basically I proved it. Okay, but when you write everything, that you say that polygon on that. Okay, now let me tell you that the technique used. Then I will talk about this. Now I want to talk about one thing, that about the technique. here I have uploaded that so that you have that question that Ali Prant is barking. So I am just giving this example. That's the problem with it. That's why I could problem. Problem number 25. This is an equicontinuity problem, page 79. Remember that equicontinuity Ascoli-Archila theorem. I don't read right now the Ascoli-Archila theorem. Equicontinuity was important. Okay. And I also talked about pointwise bound. This problem, I am telling you that right now you don't have the problem, but I am telling you the problem. So here he is saying, suppose x pointwise bounded, you know that. Suppose you have this x. X is a topological space. And this is called pointwise bounded for each x belongs to x. This collection is bounded in R. It's called pointwise bounded. Now here in this thing he is taking connected space. This is only equicontinuity. Ascoli-Archila theorem is not here. Connected space. Okay. And he is taking, instead of F, he is taking this A. The notation. A is an equicontinuous subset of Cx. You should do this problem because I have not decided yet whether I should pick up a part of this problem. So you should, but I am telling you how to do it. It should be difficult. Okay, equicontinuous. So he is saying, suppose for one point there exists x naught. This is, look, one hypothesis connected, is a subfamily, equicontinuous, of course non-empty family. Also, he is saying there is one point, another hypothesis. There exists x naught belongs to x such that this is such that fx naught, fx naught, yes, fx naught, if belongs to this is bounded in R. Okay, he's saying so that for each point it is bounded. So this is hypothesis, this equicontinuous and this for one point, and show that fx, this is x naught, fx f belongs to this is bounded for each x belongs to x. Now look, that is for each. And what is the role of this? Let me tell you that. What is the role of this? I'm saying the technique that you have used here. Here you take equal to this. X belongs to x such that you put this, such that this set, another set you take. Fx it belongs to x, this x is bounded. This is the property that you are taking those x for which this collection of points is bounded in R. You are picking up those x. Now look here, this hypothesis has nothing else to do other than to say that E is non-empty. This is the only role. So don't confuse Don't try to mix up anything else. This is only that I am telling you. This is given. That means we have been given E not equal to empty. I have taken E equal to those x such that this is bounded. So this says that E not this hypothesis. This hypothesis only says this. Okay. Right now, by using equicontinuity, you will prove is both open and closed. That means E is closed in X. Here you need this. You need equicontinuity. Look, right now I have not used equicontinuity. You need equicontinuity. That means you will have to show open and closed. It's a bit long, but it's not difficult. Now you will use connectedness. E equal to X. So that you get E. So that this thing is only to ensure that E is non-empty. That means you can say this result for a connected space. You can say this result that either this family, in a family, equicontinuous family, is nowhere bounded, nowhere pointwise bounded, or else it is pointwise bounded for each x. Okay, because if it is bounded somewhere at some point, then it will be bounded all the points pointwise, or else it may be empty. It may be empty. Okay, so that is the thing. The technique is same. Okay, so that I think we should be able to prove it. Now let me tell you that about this polygonally connected and that it has got. I want to prove this result basically. First is that complex analysis. That other result will be see that you see that last page 15, result 2. I will upload 4 pages from Conway's book. So let me which pages I will do. Conway functions of one complex. This Indian edition is available. So it's from the back direction, page 100. $300, 305. And I will upload it. I have that. Page 57. In fact, just now I give the proof that C implies A, that if that is connected, this will be polygonally connected. C implies A. You may know the last lecture, theorem 11, that is taken from here. The idea theorem 2.3. This proof is okay. So that these 3, 4, 6 pages I will upload. But why I'm doing it, I look at page 37, that result, that what he is doing. Page 37, he has taken this thing. Page 37, this proposition. Proposition 2.10 is saying if C is open in C, open and connected, in C, complex, and right now I am not talking about analytical. The differentiable will be all right. That will derivative exists. Is differentiable you don't need big term analytics. Basically, derivative exists with differentiable for all z g such that f prime z equal to 0 for all z belongs to g. Then f is constant on g. What is that? Okay, f is constant on g. That means to understand that you have this thing. This is connected open without boundary. You take this thing, complex valued function. This is your g, and such that each point you have the derivative exist and derivative is 0. Then function is constant. Okay. Now, why I have given you this thing? That let me tell you that when you do this, basic thing is you have Rolle's theorem, calculus of one variable, one real variable, mean value theorem. Okay, there you have, you can take open interval. If you have this thing, of course, if you have take this, then the one-sided derivative. Suppose you have differentiable and f prime x is 0 for all x here. Okay, then f is constant. Actually, you prove it by mean value theorem, but you should know mean value theorem proof it depends on Rolle's theorem. So ultimately, it is Rolle's theorem. So, in fact, whether you do complex analysis or functions of several variables in Rn, this is the only result you have. You will have to use this result. If you don't use this result, that means your proof is incorrect, directly or indirectly. Now look, this result we are going to use. How we are going to use it? Okay, that's why they connected. This comes here. In this problem, he is saying, suppose now look here. This page is this is an appendix page 30325. Appendix A. He's saying calculus. Title of the appendix A. This is appendix A. This is calculus for complex valued function on an interval. Interval means interval in R. So this is the thing. And here he has proposition. Okay, that you should look. Proposition A.3. If a function, the same way we can derive, the way we define derivative for real valued function of a real variable, same way I can define the way you have defined also derivative for a complex valued function of a complex variable. So here I want to have a derivative. You can define derivative of a complex valued function. Complex valued function of a real variable. So here he is saying if a function if B C is differentiable, that means derivative exists. It is differentiable and f prime is 0 for prime x, because it is I am taking the real value. So that prime x is 0 for all x belongs to AB, then f is constant. Well, proof is simple. If you use that mean value theorem, that here f prime equal write basically two functions, fx equal to gx plus I hx, where g and h are real valued function of that. You can, so that here derivative also you can prove that you can define this way also. You can define straight the derivative, or then you can prove that, or else you can take that it will be g prime x plus I h prime x. Okay, so that if you have 0, then both real and imaginary part will have to be 0. So g will have to be constant, h will have to be constant. So altogether it will have to be constant. So he is basically using this way to prove that. Now here, now look here, coming back to this page 37. Now look here. Yes. Here the connectedness, look the right. This will I will actually use polygonally connect. Now here I want to prove that f is constant. That is what I want to prove. He has taken the same technique. He has taken a subset, defined a subset, and then he showed it will have to be equal to the whole G. Okay, that you can do that way he did, or also else, but it's the same thing. Or else what I will do, I will do this. What I will do. Suppose in the G you take any 2 points. Take any 2 points. So I know this is polygonally connected. So this is this. Okay. Suppose this is your Z0 and this is Z1. Now look, this is the line segment. So this will be actually image of something interval here coming through this Z0. You take Z prime. So this is Z1. So this will go to this this. Okay. Such that you will go to Z0, you will go to Z1. That you know how to do that. You will do this. If you take t equal to 0, wait a minute, I was doing the right thing. ABKQI. Line segment I was taking here. So this will be 1 minus t Z0 plus t, call it Z1. This t at t equal to 0, it is coming Z0. At t equal to 1, it is coming Z1. It is in between the points. Okay. So ultimately function down to look what I am doing. So look here, we are having geometrically it is evident. Only thing then you will have to be able to write properly in that. That I will tell you. AB going to this. and then your function is defined, so it is f. It's going to C. This is f. Call it, you can call it phi, that function. Phi t equal to this. Okay. So that f dot phi, this is a function from here. So that means I am getting complex valued function of a real variable, and that's the appendix I have this. Now that I told the extension of mean value theorem there, Rolle's theorem there. Okay. I should not take that mean value theorem because here he has given that constant will be always there. Okay, like that I told you. But mean value theorem in Yan is not valid. So actually I am taking only that part. That I can prove. The Rolle's theorem using that I can prove. So that here you have a complex valued function of a real variable. And then I will use that. So that what I will show that here, that actually f z naught equal to f z, showing that f is constant here by using this thing. Okay, right? In fact, he has proved again, he has proved in that. Look here, he has proved a phi t will be this proved. This is differentiable than that. Okay, in proposition 8.4. That, but you can do it directly. That what is saying that a prime phi t and then phi prime t. Okay, that is it. You can use it directly, but you can use it or you can prove it. The idea is that I prove this. I prove actually f is constant on this, basically in the interval, so that f comes constant here. Now look, so f is, then I use the same thing to prove that this is constant here. Okay. Now look here, if you take z2, so fz2 will be fz1 and fz1 equal to fz2. So that z2 fz2 will be equal to fz2. This way you continue. So finally, suppose this is zn equal to this. So fz prime will be fz. That's the way you prove that constant. So basically, I want to prove it. You need to prove it in one line segment. Like that. Okay. That exactly in page 37. Now look here. You take this z1 so that if I get time, I can write it and upload it. Now look here, so that here, look at this. Actually, it will be won't be AB. It will be what? It will be 0, 1. That's how I was thinking. Okay, this will be 0. Now look here. In z equal to coming phi t is this, which is we call it zal z. It is here, zal z. Okay. Now look. Define music always notation. Define gt equal to f1 minus t z naught plus tz. That is where I am defining g actually. I am defining g from 0, 1 to c in terms of f. Okay. Some people say it's a function of f is a function of t and that. F is not a function of t. F is a function of z. Z is a function of t, like here. So this I am doing. Gt equal to this. Look, this is here. This is in the line segment. So just now you don't need to concentrate. You can think. You can erase this. You just concentrate on one line segment. Define gt. So now look, g is a function of complex valued function because it is complex valued function of 1, real variable. Now if you take derivative, look, I can prove the derivative exists. Again, you should remember from your calculus, undergraduate calculus. Many things valid here also. Look, when you have two limits exist, then the product limit will also exist. But product limit may exist without individual limit being exist. Like I'm just giving you for the sequence that. Look, n into 1 by n. This is always 1. So its limit will exist. But its limit is going to go to 0. For a sequence I'm taking, similarly you can do for function. But this limit doesn't exist. But if individual limit exists, then the product limit exists. Okay. So that here, so that is the important. Now look, what I am doing, look, GT minus GS. I am doing calculus basically. T minus 6. Limit t tends to s. That means I am taking the derivative, trying to find out whether the derivative this exists or not. Okay, right? That I am doing. Okay. Now look, what I am doing it. I am doing this. I have taken the manipulation from on which Zt minus Gs. Now look what he is doing here. He is doing t minus s. Look, in the limit concept, t tends to s means t is never equal to equal. This is the definition in the limit process. So the t minus x makes sense. Z1 plus s minus t Z2. Okay. This is negation of that. You should be careful. If I make mistake between Z1 and this, I am giving you back here. Okay. You can see that here GT. GT means matlab this. So if you take this minus this point, okay, so this point you should understand that what I'm saying, that 1 minus t z0 plus t z1 minus, to take 1 minus z naught minus s z1. So I have, until the value is here, so I am taking the difference. So this will be actually t minus s z1 plus s minus t z0. Okay. Now look, I can separate the limit because this is nothing but derivative of that. Derivative exists and is 0. Okay. So that this limit exists. Limit of this t tends to s exists because actually the derivative of f at that point s. Okay. Corresponding to s. That means z1. Okay. And this limit also you can exist. T minus s, you can see it will be nothing but z1 minus z0. Okay. Z1 minus Z2. So this will be limit of this and this will be limit t minus s, this is z minus z1 not equal to z0. So this is not equal to 0 anyway. But this is the derivative of what? This is the derivative. Okay. So this is actually coming g prime s. The derivative exists because of this. G prime s exists because of this. Also g prime s is 0 because here everything is 0. Okay. So that this is 0. Got it? Look at this function g. And I have got g prime s is 0 for any s here. That means g is constant here. But if g is constant here, mean matlab kya hai? G, if G is constant, means that means G0 equal to G1. But G0 means what? Just look here. G0 is nothing but T equal to 0, Fz naught. And G1, this is 0, Fz. That exactly I needed to prove. That's it. Okay. For the line segment I proved. Now it is polygonally connected. That I am using. But what he did, his proof is little bit different. What I was taking the technique. Okay, but you could use this because he is talking about this in, okay, or you can use his proof to straighten that. But basically, essentially same. So this is the, okay. Make sure you understand the proof. Okay, right. I have told you everything. Now look here. That problem. Result 1 is saying same thing you can prove like that. It is an Rn. This open connected again because it's a nonlinear space. C is a nonlinear space, so we can use that theorem 11. So this is polygonally connected. Okay. Now here they're saying f has continuous partial derivatives. Here I don't need to assume continuous because automatically continuous. I am assuming partial derivatives are all 0. Okay. So you have G domain, you have a function, and you have this is R. Partial derivatives are all 0. So partial derivatives is continuous. So it is differentiable. Okay. Differentiable matlab then you can write what I'm saying. Look, TF differential. It is written that del F, del X, dx, del F, del Y, dy. This will be the differential. This is defined. So in particular df, dt. Actually, it will not be f, it will be the combination of that function that I am telling you what. So this is partial derivative dx dt fy dy dt. See, we need, look, I am taking a function of two variables actually. I am taking n equal to 2 just for, okay. So here you should also have that some conditions. X is a function of t, y is a function of t, one parameter. So this function will be, actually it will be short of this. G. What's yt? Then you will get this. So if you call it phi, so actually this should be f phi. Call it phi function. Okay, so it should be this. So ultimately it will be a function of one variable. But here I said that put the comment that also Thomasson field. You need some differentiability of a, that is will be guaranteed. But you need some condition that is given is this is the chain rule. I am giving you the proof of the chain rule. And you should look at any undergraduate calculus book that there is some conditions given here that they will have to be differentiable of that. Otherwise, this derivative won't exist. Derivatives exist. Now we are having the partial derivatives. So this is 0. Again, you do on a line segment. So partial derivative 0, that means this function. This is the function of one variable, one real variable. Okay. So that you get that. So that again by the argument I have given it, it will be constant on the line, and then you have the polygonal. The technique the previous result is same. Okay, make sure you understand that. Okay, chain rule also you need that polygonally connected. In your undergraduate calculus, they couldn't talk about the topological concept connectedness, that they are taken polygon connectedness. That is equally works well. And that is very nice. Okay, right? So that I think this is all right. That I told you the proof of that. Okay, let me tell you that. Since I'm already getting late and that you use the bunch of, but let me tell you that this is about what you should read. Your first preference, the priority. These nodes, first of all, you must read carefully. At least this. Telling you one, different types of, including the proof, different types of compactness. You don't need to bother about subnet. I won't ask anything about subnet. I think here I defined subnet. So subnet you can omit. And subnet, I told you the definition if you take Kelly's definition. That I see that I posted an article on it. That's a very good article that you should read whenever you find time. So that different types of compactness you should, and then here it may omit net characterizations. It is compact if and only if every net has a cluster point, which is equivalent to finite intersection point. That is theorem 1, net characterization of compactness and Tychonoff product theorem. Look at the proof of Tychonoff product theorem by assuming Alexander subbase theorem. I have not set up I may give the proof of this by saying you can assume Alexander subbase theorem. This is very important. Okay, all of them are important here, and then connectedness, everything what I have taught, both nodes. I put into 2 installments, that's why I'm writing both nodes. Carefully, everything. So connectedness and question paper I have given it to an idea that how I set up the question paper. And here, so these 3 nodes you should read carefully. Out of 60 marks, if you are good here, you will score at least 30. That much I can tell you. I am not saying you will stick at 30. You may get more, but at least you do that. Okay. So now from Wheeler, again I have actually gave the solutions in there. Also talked about. But you can ask more if you want again. But these problems for connectedness you should do. Let me tell you. Find out. Yes, we learned page 196. Let's say problem the 26C, okay, 1 and 2. Number 1 and 2 that you should do. Okay, right. This is important. And 26E, all the parts. Actually 3 parts I talked about. Only the last part I didn't talk about. So number 1, 2, 3, 4. So here I should tell you the S1 It's a subset of R square. This is called one-dimensional sphere because R square is sphere, not the disk, not the ball. Look, if you take whole thing, that is this, and if you take this, basically this sphere means S1 means here actually it's a circle. Circle, unit circle. Here we talk about sphere. It's one-dimensional sphere, though it is in two dimension, because I told you in R square, if you take like this, just the line, that basically looks like one dimension. The people sometimes say that one-dimensional sphere, but actually it is circle. Similarly, Sn will be in actually Rn plus 1. So there it will be actually sort of like ball, like you get a square. Sorry, not ball. It will be sort of the surface, the sphere. Okay. Surface of the sphere, not ball. There is a distinction between sphere and ball. So a square in this. Okay. Sphere is the surface of the ball. Okay. So here he is saying that whether S1 Sn, they will be homeomorphical. All I can tell you, they can't be homeomorphic because you should see that it's a circle. Usually in other things you delete one point, but if you here delete 2 points, if you delete 2 points, then need 2 points, so it becomes disconnected. Whereas for this, you can see that if you delete 2 points, still it will remain connected. Actually, it will remain path connected because of those 2 points you can always bypass. Okay, so that this is important. I am telling you because if you appear for some competitive exam, in India, you may maybe ask these questions. Okay, so that make sure that here also this I have done. One problem I have done. 26H, both 1 and 2. 1 I have given in my notes. 2 is saying the polynomial of odd degree, it has a real root. Okay, if you have a polynomial function of odd degree, this is very important. Then it has got at least one real root. Basically, it is so-called intermediate value property, but it is intermediate value property comes from connectedness. So this also you should do. Okay, right? So I think I have taught everything on that. And subnet, again I am telling you, you should read that note. Okay, subnet, let me just tell you briefly that we learned the definition of subnet. I'm just talking about the subnet. He has taken 2 conditions. First condition, that increasing. This is the thing. And B is called co-final like that. Here the Kelly has put a stronger condition here. That from the note you see that footnote, stronger condition. He didn't require this condition. But the point is that if the idea to generalize subsequence, the idea is to generalize subsequence. Okay, then this also is valid. It also generalizes the idea of the subsequence. But the point is that apparently it is stronger, but it is easier to work with only one such condition rather than 2 conditions. So that's why the Willard's definition of subnet is a bit inconvenient. In fact, I don't know, except Willard, and Willard, Moncrief has picked up from Willard. That is written in that article. But other books, they follow this definition, that co-final. That you should read. That basically says, okay, let me tell you what it says. Okay. Willard says that for the condition B, that given, look, you have first of all a D directed set, net. This is a directed set, just and then you have another directed set. And there Willard has said this is increasing, this is a function A. And this gives you the net. So that the subnet will be given by f dot phi. That Willard is saying phi is increasing and phi is cofinal means if you, that means you never stop by phi. So if you give me lambda belongs to D, so they are given lambda belongs to this, there exists mu belongs to M such that phi mu is bigger than, I'm using that direction with this lambda. There exists mu. That means the image, when you go for this, basically they never stop intuitively. Whatever lambda you choose, you will always get on the right of that. That's the thing. Okay. Willard with this put phi is increasing. That is also challenges the concept of the subsequence. That's the idea. But point is what Kelly did, this is only one thing. That here, look. What he is doing, Kelly is saying, given lambda belongs to D, there exists mu naught here, given lambda belongs to D, let me see. There exists this such that there exists mu naught belongs to this such that phi, it was there, phi mu naught. Okay. But here, given there exists mu naught belongs to M such that phi mu greater than equal to lambda whenever this. Look here, increasing, if you have increasing, then it will be alternative. Then phi mu will be greater than equal to phi mu. So if you have the Willard, obviously you have the Kelly's thing, not the other. Phi mu will be greater than, then it will be okay. If you have this, then phi mu greater than equal to phi mu naught, so phi mu naught. So if you have Willard's condition, if you have Kelly's condition. But if you have Kelly's condition, you don't need to have Willard's condition. So that here I am doing this. Given the lambda belongs to, there exists mu naught belongs to such that whenever this. Here earlier I am doing only for one. Here I am doing whenever you have this. That's the difference. And but in Kelly now you have only one condition for this subnet. But look, since increasing sequence of the way subsequence is defined, that was the increasing thing. So it automatically it will be satisfied. So people usually use this thing. So Kelly's note that you'll have to see that. Okay, right? Fine. And so that, but I am not going to give you the subnet, but you should read the article on net I have uploaded. You should read. You don't need to go through all the proofs on that, but at least you should understand the concept. That is very important. Another thing, last thing I would like to tell you that about final exam, I think somebody has written to me that final exam, major exam. that they don't want on 6th April, I think April 10 or 12. But I am telling you, who is your coordinator? Tell me, who is your coordinator?
Sir, and Surjit Kaur, ma'am.
You should ask her whether, because it is not, it won't be online, so I can't change the date, because the room has to be available. Okay, so that's why it's not up to me. It's like, because she can talk to the administration, so I don't have any problem. Whatever date you choose, whatever time you choose, okay. But you should talk to Surjit Kaur. Okay, just ask her that whether she will send email to them and they will try to. Okay, I don't have any objection to that. Okay, but it's not I can do it. Okay, right? She can do it. Just ask her. Okay, see, and I think you'll have a good exam whenever you do it. But you should let me know that whether you have talked to Surjit Kaur and you have changed the date, because I have asked one of my ex-students, PhD students, who did PhD. She teaches in St. Stephen's. She will come. She's supposed to come on 6th April after the exam. So the otherwise, then I'll have to. If you change the date, I'll have to tell her not to come that day. Okay, so it's up to you. It's up between you, your class, and Surjit Kaur to fix that. Okay, you can tell Surjit Kaur that I do not have objection. She can verify by sending an email to me. Okay, that also told you. You can tell her that she can check with me by sending an email. I will confirm. Okay, see you. Bye. Best of luck. I won't take any more class. Okay, but I will upload to Conway's 6 pages. I said that I will upload, but that I have basically talked about everything. But still, you can read that. You should read. Okay, and I won't take any more class. I will meet you in the exam.